Start.
Now, after studying Kirchhoff's voltage law and Kirchhoff's current law in the current electricity, we will move towards our very important article, that is Wheatstone's network. It is very important article as compared to examination point of view. This Wheatstone's network, this is the circuit diagram for Wheatstone's network. Physicist Charles Wheatstone in 1843 developed this network to determine the unknown resistance accurately. So, what is this circuit consist? So, this circuit consists of 4 resistors: R1, R2, R3 and R4 connected like a quadrilateral. Connected like a quadrilateral as shown in figure in the form of quadrilateral. So this diagram also consists of sensitive galvanometer G, which is connected between 2 vertices of the quadrilateral, that is in between B and D. So other 2 vertices of the quadrilateral A and C. So the vertices A is connected to the positive terminal of a battery, and the vertices C is connected to the negative terminal of a battery through K. Now, while to study the working of this Wheatstone's network, we will just take in account how current divides it. Now, suppose as soon as you close this K, the current will start flowing through the battery and the current will come at the point A. Now at point A, the current will divide into 2 parts, that is I1 and I2. Current I1 is flowing through the resistor R1 and the current flowing through the resistor R3 will be I2. So after closing the key, it will happen, means current will divide into 2 parts. Suppose the path ABC, here the point B, and on path ADC of the bridge, there will be a certain point D such that it has the same potential as that of B. Suppose D is a point which is on the path ADC such that the point D has the same potential of point B. If such thing will happen, means point B and point D will have the same potential, then in that case there will be no current flow from point B to D or from point D to B. Why it will happen? Because we know current will flow only in between those points which has potential difference. If these 2 points will have same potential difference, then there will be no flow of current in between that 2 points. So what will happen? Because of that, the current I1 flowing through resistor R1 will not divide in this part, so it will go as it is. Same current will flow through the resistor R2, that is I1. If these 2 points B and D has the same potential, then there will be no division of current I2 further, and the same current I2 will flow via resistor R4, and the current flowing through galvanometer will become 0. So this is a very famous condition, and that condition in this Wheatstone's bridge is called as balancing condition, or this condition is also called as balanced bridge. So when we say the bridge is balanced, when the galvanometer is connected between 2 points such that these 2 points will have the same potential and there is no current flow via galvanometer, then this condition is called as balanced bridge condition. So when bridge is balanced, then it will follow a certain relation, a certain equation, and that equation is called as R1 upon R2 is equals to R3 upon R4. When bridge is balanced, then in that condition, the ratio of these 2 resistors, R1 upon R2, must also equal to the ratio of these 2 resistors, that is R3 upon R4. This case is satisfied by the Wheatstone's bridge in balancing condition. So while studying this balancing condition and its proof, I will once again repeat the construction to all of you. This is the Wheatstone's bridge developed by physicist Charles Wheatstone in 1843. It consists of 4 resistors R1, R2, R3 and R4 in the form of quadrilateral. The two vertices B and D, in between two vertices B and D, a sensitive galvanometer is connected, and other two vertices is connected to a cell through TK. As you close the TK, a current I starts flowing through the circuit, and this current is divided into I1 and I2. Now, suppose the point B and D has equipotential point, then there is no flow of current via galvanometer, and same current I1 will be flow through R2, and same current I2 will flow via resistor R4. And if such thing will happen, then the bridge is said to be in balanced condition, and in balanced condition, every Wheatstone bridge will satisfy this equation, that is R1 upon R2 is equal to R3 upon R4. Then we have to take how this condition is satisfied by the balanced Wheatstone bridge. We will take the proof of this final equation, how this condition will achieve in balanced bridge condition. So before going to the proof of this Wheatstone's bridge, I will mention some point to clarify your doubt. That point is like that. Some student asks, sir, what will happen if bridge is not balanced? Suppose some student asks, suppose sir, B and D will not have equal potential. Then in that case, what will happen? If point B has higher potential than point B, than point D, then current will flow from B to D, and the Wheatstone's bridge in this case will not be balanced. So if point D will have more potential than point B, then current flows from galvanometer via galvanometer from D to B, and in this case also the bridge is not balanced, and then we cannot say that R1 upon R2 is equal to R3 by R4. We can say this condition only if when there is no current flow through the galvanometer. This is the very simple case. So we will study only balanced condition case of the Wheatstone's bridge. So to take the proof of this equation, we will have to apply some mathematical treatment, and we have to apply Kirchhoff's voltage law to this Wheatstone's network. After applying Kirchhoff's voltage law, you will got this equation for balanced condition. So we will take the mathematical proof of this Wheatstone's bridge for balanced condition. So while taking proof, we must know here I is equal to I1 plus I2. The total current, when bridge is balanced, the total current is the summation of I1 and I2, because there is no flow of current via galvanometer. Now in this case, apply Kirchhoff's voltage law to the loop A, B, D, A. Apply Kirchhoff's voltage law to the loop A, B, D, A. Now you know Kirchhoff's voltage law. We have also taken sign convention for KVL. So as we move from A to B, the direction of current and direction of tracing of loop is same. So that is why this potential drop I1 R1 will be taken as minus. Why minus? Because current has the same direction as that of the loop. Now as we move from B to D, here galvanometer has some resistance, but Ig is equal to 0. Therefore, this IR drop through galvanometer will be 0. Why 0? Because Ig has the value 0. So Ig into G becomes 0. So this is the while moving from B to D. Now as we move from D to A, we observe that current is flowing in the downward direction and we are moving in the upward direction. It means that the direction of tracing of the loop and direction of the conventional flow of current is opposite to each other. So therefore I2 will be treated as positive, and I can write here I2 into R2. So this is equals to 0. This is the equation that we got here, and just rearranging the terms, we will get I1 R1 is equals to I2 R2. This is equation number 1. This equation I have got here after applying Kirchhoff's voltage law to the loop A, B, D, A. So this is the first case of KVL. Sorry, the first case of Wheatstone's network. Now similarly apply KVL to the another loop B, C, D, E. Apply KVL to loop B, C, D, A. To the loop B, C, D, A. Now, as we move from B to C, the direction of loop and the direction of current is same. Therefore, here we can write minus I1 R2. Minus sign because direction of loop and direction of current is same. So therefore, this IR drop is treated as negative. Now, as we move C to D, we observe that the direction of current and direction of tracing of loop is opposite. So that is why this IR drop I2, I4 will be taken as positive. That is I2 R4. Now, as we move from D to B, D to B. As we move from D to B, so we observe that here galvanometer has some resistance, no doubt, but current flowing through galvanometer is 0. Therefore, here we can write 0. That is equals to 0. So from this equation, we will get I1 R2 is equals to I2 R4. So equation number, this is equation number 2. So this equation first and 2 I have got after applying Kirchhoff's voltage law to the first loop and to the second loop. Now here divide equation first by equation second. Divide equation first by equation second. After division, you will get here. First equation is I1 R1 is equals to I2 R3 divided by second equation is I1 R2 and it is I2 R4. Okay, this is I2. Okay, so here I1 will get cancelled, I2 will get cancelled, and we will get equation R1 upon R2 is equals to R3 divided by R4. So this is the proof. After applying Kirchhoff's voltage law to the both loops, first loop and second loop, and just rearranging the terms and dividing equation first by equation second, we got the proof, that is when bridge is balanced means there is no current flow through the galvanometer. In that condition, the ratio of R1 upon R2 to the ratio of R3 by R4 is equal, and this is the condition and this is the proof of Wheatstone's network in balanced condition. This is very simple proof. It is regularly this question is asked in examination. So many numericals in NEET examination, in JEE examination will be asked on this question. If you out of these four resistors, if you know any three resistors, suppose if you know R1, R2 and R3, then with the help of this equation you can calculate the value of unknown resistance R4. If you know, if you have known resistance R1, R2 and R4, and if you have unknown resistance R3, then with the help of this equation, by putting the known values, you can calculate the value of unknown resistance R3. So this is very important aspect to find out the unknown resistance with the help of Wheatstone's network. So many students ask me, so what will happen if we replace the, if we put this galvanometer instead of BC to arm AC? If we interchange the position of cell, this cell E and galvanometer. If we apply cell and key to this arm and galvanometer instead of using in the arm BD, if we use galvanometer to this arm AC, then what will happen? Will this Wheatstone's network will work after interchanging the position of galvanometer and cell? So the question to this, the answer to this question is that it will definitely work if we interchange the position of a cell and galvanometer. Then also this condition will be take place, they will be balanced, and it will also work for that conjugate for that arm also. So therefore these arm BD and AC are called as conjugate arm. Means you can interchange the position of cell and galvanometer in the Wheatstone's network. So this is a very simple proof. Now there is also another alternative method to achieve the proof of this condition, that is R1 upon R2 is equals to R3 by R4 with the in case of Wheatstone's network. So this condition, this proof or this final answer I have obtained with the help of Kirchhoff's voltage law. If I want to prove this condition, balance condition, with the help of Ohm's law, then it also can be proven with the help of Ohm's law. So we can also prove the same result with the help of Ohm's law. So we will just study the proof of this Wheatstone's network with the help of Ohm's law also. So I think there is no need of repetition of proof of this Wheatstone's network, that is condition, that is R1 upon R2 is equal to R3 by R4 with the help of KVL. Now we will move towards the proof of this Wheatstone's network balance condition with the help of Ohm's law, and we will take that proof. Or proof of balanced condition using Ohm's law. Using Ohm's law. So, while applying Ohm's law, you know, when bridge is balanced, the potential of point B is equal to potential of point D. We know when bridge is balanced, the potential of point B is equal to potential of point D. So we can write this equation as VA minus VB, means potential of point A minus potential of point B is equal to potential of point A minus potential of point D. So we have just taken VB means here VA minus VB, and VD means VA potential of point A minus potential of point D. So we know VA minus VB means I1 R1 is equals to VA minus VD means I2 into R2. Similarly, this equation first can also be written as VB minus VC, and it is also equal to VD minus VC. This equation we can write like this also, and this equation 1 we can write like this also, that is potential of point B minus potential of point C is equal to potential of point D is equal to potential of point D minus potential of point C. Means this potential in this equation, first we have subtracted VB and VD from VA, and in the second case from VB and VD we have subtracted VC. Okay, so we know here potential of point B minus potential of point C means I1 R2, and here VD minus VC means I2 into R4. So it is I2 into R4. So this is equation 1, and this is another equation second. So just divide equation first by equation second. You will got the equation here I1 R1 is equals to I2 R3 divided by I1 R2 and I2 R4. Just here I1 will get cancelled, I2 will be cancelled, and we will get the final equation R1 upon R2 is equals to R3 by R4. So this is the proof of Wheatstone's network for balanced condition. When Wheatstone's network is balanced, then the ratio of the resistors, that is R1 upon R2 is equals to the ratio of resistor R3 upon R4 is equal. So this is very important aspect, that Wheatstone's network is used to determine the unknown resistance very accurately, and for that we have to balance the bridge, and when the bridge is balanced, this condition we obtain, and we have taken the proof of this condition with the two different methods. First proof we have taken with the help of Kirchhoff's voltage law, and second proof that we have taken with the help of Ohm's law. In examination you can write this with any method. If you ask precisely with some method, if they have given obtain the proof of this Wheatstone's network, balance condition Wheatstone's network with the help of Ohm's law, then you can write this method. Or if you ask in examination with the help of KVL, then you have to write the previous method that I have explained to you just. So with the help of this very small and short article, we move towards our next article, and that article is also important. That article is the modification in Wheatstone's network, and we can we have family with that devices also, that is meter bridge. So we will take that article just in a very short time.
Start.
Now after completing our Wheatstone's network, we will move towards next article from this lesson, current electricity. That is the article is meter bridge. So there is no much more difference in Wheatstone's bridge and meter bridge, because meter bridge works on the same principle. Meter bridge works on the same principle of Wheatstone's network. If you observe this diagram, so you will get very much clear idea what is the difference between the Wheatstone's bridge and meter bridge. So here, if you look towards the diagram, you find that there is two thick copper strips, three copper strips. First strip is C1, second L-type copper strip is C2, and third thick copper strip is C3. These copper strips are mounted on the. Now a wire, a uniform metallic wire, conducting wire, is stretched between two copper strips C1 and C2, which having a length of 1 meter, exactly 1 meter. So this conducting wire is stretched between two L-type thick copper strips C1 and C2 having length 1 meter, and third copper strip C3 is placed in between two L-type copper strips C1 and C2 such that it forms two gaps in the meter bridge. First gap is known as here left gap, and second gap is called as right gap. This first gap contains unknown resistance X, which we have to calculate, and second right gap contains resistance box, means a variable resistance box in which we can vary the resistance, and a very sensitive galvanometer is connected to the point B, and the second terminal of galvanometer is connected to a jockey. What is jockey? Jockey is a metal rod which has a knife edge at the bottom, and which is used to tap the wire A to C to take the different readings while performing the experiment. Now the point A from copper strip C1 is connected to the positive terminal of a battery, and the neutral terminal of a battery is connected to the point C via key K and rheostat RH. This is very simple construction. So the function, the working of Wheatstone's meter bridge, it is also called as meter bridge, also called as Wheatstone's meter bridge, is same as that of Wheatstone's bridge. It works on the same principle. It is also used to calculate the value of unknown resistance accurately. Only the modification is that it uses a 1 meter long uniform conducting wire in the meter bridge. So therefore it has a length of 1 meter. So that is why it is also called as meter bridge. So the unknown resistance is connected in left gap, and the variable known resistance, that is resistance box, is connected in right gap. A uniform metallic wire AC is connected between two copper strips. The cell is connected, key is also here connected, and rheostat is also connected. And this is the complete circuit diagram for the meter bridge. Now we will take working. How it works? So as soon as you close the key K, the current starts flowing through this circuit R. Now at the point A, the current is divided into two parts. Some current flows through resistance X, RB, via C2, and some part of current is flowing through the wire AC, and it will come towards negative terminal. So this is the simple working. But to take the perfect reading, we have to make some adjustment. Before closing the key K, you have to withdraw a certain value of resistance from resistance box, and you have to adjust the value of rheostat such that the deflection that shown by the galvanometer, it should be in between 1/3. It shows the deflection in between 10 to 20 division. Why this I am telling to you? As soon as you close the key, you have to tap this jockey to the end A, and you have to tap this end of jockey to end C. After tapping the jockey to end A and end C, you will, if you observe the deflection in the galvanometer in the are on opposite sides, then your connection will be okay. Okay. Once again I will repeat. As soon as you close the key, and as you remove certain resistance from resistance box, and if you adjust the value of RH such that on touching the jockey to point A and on point C, you must have to plot the deflection on opposite sides of the galvanometer. If it will happen so, then your connections are okay. If it will not happen, so you check your connection. If somewhere some loose contact will happen, then tight that contact and once again try. Okay, so I assume that you got the deflection in the galvanometer on opposite sides. Then what is the next procedure? Now you just move this jockey from point A, either from point A or either from point C. It depends on your choice, but I will prefer that you tap the jockey from point A on towards what we can say right hand side. Now check the point at which the galvanometer shows zero deflection, or you can say that null deflection. Suppose at point D you observe that the deflection in the galvanometer becomes zero. Once again I will repeat. You started the sliding the jockey or tapping the jockey from point A to point C, as you are going from point A towards point C, and at a certain point D you have observed that the galvanometer showing the deflection equal to zero, means null deflection. At that point you have to stop the moving the jockey, and you have to just mark this point as a D. Galvanometer shows null deflection, means in that case the point B on copper strip C3 and point D have the same potential. If these 2 points will have the same potential, means we can say that the meter bridge is balanced. Balancing condition we have got here. Now in this case, the resistance of the ratio of resistance of X to the resistance of R, and the ratio of resistance of length Lx to the resistance of Lr will be same. So this is the balancing condition, and this balancing condition can be written as X by R is equals to resistance of length Lx. This A to D length is called as Lx, divided by resistance of length Lr. This is the length Lr. D to C length is called as length Lr. Means as soon as you got the null point in the galvanometer, you have to stop the jockey there, and you have to equate the ratio. Means the unknown resistance divided by known resistance from resistance box. This ratio is equal to the resistance of length Lx divided by resistance of length Lr. So here we can write X by R is equals to, suppose lambda is the resistance per unit length of the wire. Suppose this wire. Suppose this wire is 1 meter long, and its resistance per unit length for that wire is lambda. So the resistance of length Lx is equals to lambda into Lx, and similarly we can calculate the resistance for length Lr is equals to lambda into Lr. Just cancel lambda and lambda. You will got X by R is equals to Lx divided by Lr. and this is the balanced condition. So to calculate the unknown resistance, we will got the equation x is equals to R into Lx divided by L. This is the very famous equation. Here x is the unknown resistance and it can be calculated using this formula. Suppose from resistance box you have calculated, you have withdrawn the value of resistance is 20 ohm, and suppose Lx upon Lr is equals to for example 40 by 60. Suppose Lx is 40 and Lr is 60. Then by putting the value 40 divided by 60 means 4 by 6 into 20 means 80 by 6 you will got your value of x. Suppose this is very simple and sophisticated method to calculate the unknown resistance using middle bridge. So this is the required expression and circuit diagram. I have also elaborated the theory. If you have any doubt, then you can ask me at any time. Just before concluding this article, I will once again repeat this mathematical expression. When you got the null point, means bridge is balanced. At that condition, you know in case of Wheatstone bridge, when the bridge is balanced, x by r is equals to resistance of this length to the resistance of Lr. This ratio are equal, and in this case lambda will get cancelled, and you will get final equation x by r is equals to Lx upon r, and here x is equals to unknown resistance equals to known resistance r into Lx divided by Lr. With the help of this formula, you can calculate the unknown resistance of any device using middle bridge. Okay, we will stop here with this introduction. Thank you.